And we are live. Hello to everybody tuning in for MCP's algorithm grind. So this is MCP's last event before ICPC tryouts, which will be taking place on February 13th. Make sure to sign up if you haven't signed up already. You can sign up at mcp-team.com/tryouts, and I think we've scattered that link everywhere. Now, the plan for today is that I found a list of questions that go through, I guess, like a variety of different algorithm topics, and we're going to look at those and I guess try and solve the questions and also learn the algorithms involved. So they should start fairly easy, but they should get like pretty fun as we move on. I don't think we'll be able to do all of them, given this is only 2 hours, but I think it should be good. So let's give it a try. Okay, and I'll say too, during all of this, I will keep, I'll keep the chat window open on the right here. So if you guys have any questions at any point in time, just throw them into the chat. I'm happy to answer them. Or if you have any other questions about MCP or algorithms or just anything at all, throw them in there. Alright, so let's get started. Our first question is a super classic. Many of you have probably already solved it. It's balanced brackets. So this is like a super classic, I guess really this is a classic interview problem, but it's worth talking about. So the idea is, we won't even read the text, we can actually go straight to drawing it out. So the idea with balanced brackets is, normally in programming you can have parentheses, and we call parentheses balanced if every opening parenthesis, which is like a left parenthesis, has a corresponding closed parenthesis. So we call this a balanced set of parentheses. Now similarly, we could have multiple parentheses nested like this. We would call this a balanced set of parentheses. And similarly, we can do things like putting parentheses beside each other or doing stuff like this. And this is still balanced parentheses. However, we don't call it balanced parentheses if we have like unmatched right parentheses like this. Yeah, so that's honestly, that's what it boils down to. So in this HackerRank problem, we have a slight variation on this classic, I guess, programming problem, in that we can have left parentheses. Actually, I'll zoom in a bit so you guys can see better. Oh, maybe a little bit less. So we can have left parentheses, but we can also have like curly braces or square brackets, and they similarly have to be balanced. So that means like something like this is considered to be balanced, but something like this is, let's do this, is not considered to be balanced, because like we have to match every like parenthesis with another parenthesis, not with something of a different type. So not balanced. Oh, sorry, I should have done a not balanced here. Okay, so let's think of an algorithm for actually like, the question asks us to determine, like given a string of these different parentheses types, whether it's balanced or not. So let's think of an algorithm that might accomplish that. So something we want to do first is simplify the problem. So we could think about it just in terms of regular parentheses first and pretend the other ones don't exist. So if we just had regular parentheses, then whenever we put down a left parentheses, that's almost like a promise to ourselves that says like, hey, at some point in the future, this needs to have a corresponding right parentheses. So we need some way to formalize that promise to ourselves of saying like we're going to have a right parentheses later. And one really easy way to do that is actually to have a counter. So you could think of saying, let's have a variable that keeps track of how many open left parentheses I have. So let's call that, I'll call it C, because I'm pretty lazy. So to start, we'll have C equal to 0. And then when I encounter, let's do this first example right here. When I encounter my left parentheses, I'll say, oh, I have a left parentheses. I can put my counter to 1. And then when I have a right parentheses, I can decrement my counter saying I fulfilled one of my promises. So now I'm back down to 0 open parentheses. Now this is a cool technique because, let's look at another good case and then another bad case and see how it might work. So if you look at this case now right here, you'll see that we have 0 to start, we do left parentheses, and we say, hey, now I'm promising myself that I'm gonna, I guess, close this one thing, and if I do another left parentheses, now I promise myself I'm gonna close 2 things, And now it's cool because when I close them, it goes back down to 1, back down to 0. That seems to work. And if, let's say, they do something illegal, like you have a right parentheses without having the left parentheses, then that's a case like this, where we go starts equals 0. If we see a right parentheses right off the bat, we say, hey, I need to decrement my counter, but my counter's at 0, so if I decremented it, it would be negative. Therefore, this must be bad. So we can say, hey, this isn't balanced. Similarly, the other case where we can show it's not balanced is if we have something like this, let's say like left, left, right, and that's the entire thing. In a case like that, we're going to go left, so 1 promise, left again, 2 promised, right, 1 promised, and then I reach the end and I say, hey, I haven't fulfilled all my promises, so this can't be balanced. So I think that's kind of a fun way of dealing with this. And this seems good. But it turns out it won't scale to a solution that works for multiple bracket types. Because, let's say just naively we try and use that same technique. I say, and let's say I'm concerned about this test case and this test case. Because that one's fun. So if we try the same technique where for like these left brackets we increment a counter by 1 and right brackets we decrement by 1, then for this one it might work, right? Our counter will go to 1 here, to 0 here, back to 1 here, and back to 0 here, and we'll say this is okay. But here, if we did the same thing, we go up to 1, down to 0, and we just say that's okay, then we wouldn't catch that these parentheses types, sorry, these I guess bracket types aren't the same. So I guess then we don't, instead of just storing like how many parentheses we have open, we need to store like what brackets we have open and like what type they are. So one sort of natural way of doing this is keeping a stack of the current open brackets. Because one insight you can make is that, let's say I open a left parentheses, and then I open some other type of parentheses. If my parentheses are balanced, no matter what I do, I'll have to deal with this guy, so I'll have to close this guy before I close this guy over here. Because something like this would not be balanced. That'd be bad. So yeah, so we can think of our implementation then. What we'll do is we'll maintain a stack of parentheses as we encounter them. And so whenever we encounter a left bracket, I should be saying bracket instead of parentheses here, sorry. Whenever we encounter a left bracket, we can push it onto our stack. And whenever we encounter a right bracket, we need to assert effectively that it matches the guy at the top of our stack, and then we'd pop that guy off the stack. And if at the end we have anything left on our stack, that means we have unfulfilled promises. And that's bad. Or if at any point the right parentheses doesn't match, or there's nothing on the stack, then that also means it's bad, it's unbalanced. So that actually doesn't sound too bad to implement, so let's try. So we see, if we look at our input here, we're given, so n is the number of strings, and then it gives us a new like balanced string of, or maybe not balanced, we have to find out, string of brackets on each line, and we have to print yes or no for if it's balanced. So let's go down to the code. I'll do this in Python, because Python's pretty convenient, honestly, for these things. I'm normally a C++ guy if performance matters, but I do love my Python. So let's go. We're going to read in int. And here's a little Python trick here. So often in Python, people normally do for loops like for I in range n, that sort of thing. But sometimes you don't really care about the variable. You just want a loop to run that many times. So in those cases, you can just put an underscore here, and it won't waste a variable name. It's not like that useful, but it's sort of a semi-handy trick. So in any case, let's see. So effectively, what is it? We're doing a different test case. Yeah. So we're reading n test cases and handling them separately. Let's encapsulate this just for fun. We'll make it really pretty. We'll go s equals input, and then let's go solve s, and we can write some nice solve function that prints yes or no. So pretty. Okay. So let's see, what do we need? We said we wanted a stack, and we said we were going to look at every character in our string, and if it's, first we want to check if it's a left bracket. So easy way of doing that is we can just say if C is in, this is sort of another hacky Python trick, you can say if C is in this string, which contains all these brackets. So it's like saying, is like our bracket character in this string of bracket characters. Sort of sneaky way of checking that. And we know we're either always a left bracket or a right bracket, so if we're in this case here, we must be a right bracket. And so in this left bracket case, as we said earlier, we're just going to stick the bracket onto our stack. Oh, there we go. Now the sort of more annoying part to code is, in this right bracket case, we have to check that we have like the matching thing. So let's make just for the sake of making this clean, I'll even do this in here. I'll have a little thing called like matching. I'll just say matching. You know what? I'll just say M. Let's be real concise here. And what I'm going to do is I'm going to store for every like right bracket, I'll store the corresponding left bracket that matches it. So with this one, I expect this one. With this guy, I expect to see left curly. And what is the... Oh, let me do this properly. Here we go. And with right square bracket, I expect to see left square bracket. Cool. That's all the cases. So now what I want to do, it'll say, if it's a right bracket, then it better be the case that... it better be the case that stack is not empty. So that length of stack is greater than 0. And let's see what else. Ooh, actually I just thought of how I wanted to do this. So to make this even cleaner, so when I implement this, I'm probably going to want to return early if I detect an error early on, but I also might return later. So instead of printing like no in both those places and then returning, I can clean up my code by just here saying print. I'm actually doing so many Python tricks this question. It's fun. I can do print yes, if solve, else no. So this is like a Python ternary statement. So it's like value, if condition, otherwise, other value. So what this will do is, if my like solve thing returns true, then that means it was balanced, and it will print out yes. If it returns false, then it will say it's not balanced, and it will print out no. So then here, when I'm doing this check, I can say, so when I'm matching something, I have to have something on my stack, and it must be the case that that thing at the top of my stack, this is a Python shortcut to get the top of your stack, or the top of your list, same thing, is equal to the matching thing for C. And if this is the case, then we just pop off that matching thing at the top of the stack. If this is not the case, then we failed already. So we have to go return false. Cool. And if we manage to make it to the end here, you might get overconfident and want to return true here. But we still have to watch out for the case where we have like unfulfilled, so we have stuff left on our stack, which means we have brackets we haven't closed. So let's return length of stack equals 0. So we only return true if our stack is empty. So this intuitively seems okay to me. Let's see if it actually works. We can run here. So you'll see I did something kind of terrible. Oh no, what did I do? Wait. Why am I mad? Okay, this is why it's fun. Let's figure out why it's broken. So sorry, 3 test cases, yes, this. Seems good. One good thing about having a chat is you guys can help me for my errors too. It's like extended error support. I don't know. So anyways, we read in 3. Let's walk through. So we read in 3. We say for blank in range 3, sure. So run this code 3 times. We read in a string, which reads in this line right here, and then this one, sure. And then we call this solve, printing yes or no. Our code prints no every time, which I guess is bad. Let's see. So what is it? We went through. Whenever we saw a left parenthesis, and those are the only 3 types, right? Left parenthesis, left square, left curly. Correct? Correct. Cool. Then we stick it on. Okay, I agree with that. Otherwise, it must be the case, like, it must be right bracket. And in that case, if there's something on my stack, good, and that thing on the top of the stack equals my matching, then we're pretty happy, and we pop it off the stack. Let me think. Otherwise, we return false. Okay, yeah, so if there wasn't something in the stack. So we're returning false too early. So we're probably hitting this when we shouldn't be for some reason. So I'm curious. Even on this first one, I say it's not balanced. Why? So left curly, left square, left parentheses. Let's think. So left curly, it's definitely in here. Wait, let's print sanity check. Ready? Let's be san for sanity. Let's see. So I should get three of those, right? San. Yeah, san. No, okay, that makes sense. And then let's just look what my stack looks like before. Should be so cool. So I had these on, I popped. I had these on, I popped. Oh no. Okay, well that's where my bug is for some reason. So when I'm processing this square bracket right here, for some reason, instead of matching it, it's saying I don't like your code and returning false. Okay, so I bet the error is, yeah. So I had a typo right here. I didn't notice it. That would be, see, one thing with the HackerRank editor is it'll sometimes autocomplete your brackets. So you'll type one and it adds the other. So here it did that, and that's what burned me. I'm quite fond of, I know Lucas is a big Emacs guy. I normally just use Vim on my computer when I write most contests. It's very fun. I know that's like super stereotypical to be like, I'm a Vim user, but it's fun. Now, sorry, you also notice we're printing our debug output, so you have to not do that. Okay, there we go. Now we pass all those, and we can submit. And if we submit this guy, we see all AC. Yeah. Okay. That's one down. To make this exciting, I've always thought the best part about competitive programming is if you're on a site like Codeforces, the problem turns green after you've solved it. So I think we got to do that here. Okay. This next one is a classic. This is two-sum. Okay. So I guess the idea here, it's very short, so I'll even let you guys read it. It's like, so you're given an array of integers, right? And you're given some integer, they call it target here. And the idea is, you want to find two integers that sum up to target. So you could think, let's even draw this out. So actually, wait, do they have a test case I can steal? Let's see. I can probably even just like, oh yeah, look at this. This is, no, just kidding. That will not copy paste. Okay, I'm just gonna write it out. Is it 2, 7, 11, 15? Okay, watch this. Okay, so we're given an array like this in this problem, and we're given some number which they call target, and we want to see if we can find two indices in here, I and j, such that like this array at I plus this array at j equals this target. And normally the constraint on this problem is that you want to be able to solve it in linear time. So we could think of how to do it in worse than linear pretty easily. So you could imagine if we had two for loops, so we could go like for I in yada yada, and for like j in like the array. So go through like every possible pair of elements and try and sum them up. But this will be on squared, which is way too slow for us. So we need to come up with, I guess, like a smart way of doing this in linear. And so the trick ends up being, and you can probably see it if you look at the hint I've put next to the question. The trick is to use hash maps or hash tables. So what we can do, so consider we're looking for two values such that they sum up to target, right? Let's call target t, and let's call our two values a and b. Then we're looking for some a plus b equal to t, right? So instead of doing this, what if we looked for some a such that it's equal to like t minus b? Now what do I mean by that? I mean, so let's go through our array like element by element, and let's consider like, hey, if I'm looking at elements, let's say like 7, right? Then hey, 9 minus 7 is 2. So I can make it if I had a 2 anywhere in the array before me. So what I do is as I encounter elements, I add them to a hash map, and then later I just want to be able to look up like, hey, do I have this element, and if so, what's its index at? So that might make a bit more sense with code. So let's actually go through that. And let me just read this too. So let's see. We can assume... Oh, okay, awesome. So we can assume there's only exactly one solution. So that makes our life a bit easier. So it looks like we're using Python here. So let's go. I'm going to call my hash map this H. It's very verbose. And now what do we say we're going to do? We said we're going to go look through every element in numbers. And we wanted to say, hey, what is target minus E? That's like what we need, right? And we want to see if that value exists in our hash table. So if this is in our hash table, then we have an answer. And we could just return... Oh, sorry. I guess I need a... So I need to return the two indices. So what I'll do here is in Python you can use this thing called enumerate when you go through a sequence. And it'll give you a bunch of tuples that contain like the index of the thing you're looking at and the value of the thing you're looking at. So it makes it easy to get both of those things just like this. So I guess, yeah, here what we're doing, we're going to say if the value I need is already in my hash map, return its index, which will be hash map at need, and return my index. And now, right now, you'll notice we don't actually put anything in our hash map, so you have to actually do that as well. So what we'll do is after processing an element, we're just going to insert it into the hash map. So we'll say hash map at, what is it? Yes, sorry, hash map at my value equals my index. And you might say, well, why don't we do this before? If I inserted it into the hash map before, it'd be possible that I could look at myself. So we could have a case like, this is a fun case. We could have something like, let's go like 441. We could pretend our target is 8. Imagine now, actually no, sorry, I'll make it even worse. I'll make it like 451, and pretend our target's 8. So this one wouldn't have an answer. But so, if we implemented our code in such a way that when I look at 4, I first put 4 in my hash map, and then I say, hey, 8 minus 4 is 4, do I have it in my hash map? I'd look up my own value, and I'd end up putting both my indices right on the same spot, which isn't allowed, since we see that, what is it? Yeah, you cannot use the same element twice. So that's why we added our values to our hash map, strictly, I guess, once we're done everything else. So cool, that seems like it would make sense. That should be all we need. So they guarantee there's exactly one solution, so at some point this should just like work out. If we ever make it here, then print sad face, our code broke. Let's run. Oh, it's gonna make me sign in. It's unfortunate. There we go. Okay. Let's run it. Oh, sorry. I used to be a big Python 2 user back in the day. Still, don't type my parentheses around my print half the time. There we go. Okay, we passed the sample. Let's do the real deal. Cool. Oh, we're pretty slow. We use like no memory though, which is nice. Yeah, so one good thing that's worth pointing out is like why this is actually linear runtime. So consider that at each step of the array, we're inserting an element into our hash table, which takes like 01 amortized time. And similarly, all the lookups in our hash table take 01 amortized time. I probably won't go through like why a hash table takes like 01 amortized time, but that is something you should look up yourself like at some point. It's like a useful thing to know. But it's pretty cool then. So we're just like inserting into a hash table and looking up in a hash table every time. So it's 01 work at each step, and there's n steps, so on work total, which is nice. So we got AC on that. So let's green this guy up. Delicious. Oh, actually, I'm really excited for this next one. I've actually never solved this next one, but I don't think it's that bad. So this one's called Peter and combination lock. So Peter is like a well-known competitive programmer who uses Java. So it's sort of a gag question in that regard. But let's see. Let me summarize the question. Okay, yeah. So basically, you're given like this gauge here, and you're given a bunch of, let me make sure I got this right. Yeah, it looks like you're given a series of n rotations that you want to apply to the gauge, and the n can only be up to 15, so it's pretty small. And these angles, I guess, are limited from 1 to 180 degrees. And so you can, for every like rotation that you're going to apply to this gauge, you can rotate it clockwise or counterclockwise. Oh yeah, I have a question that, or not a question, but in the chat, Osama is like, I haven't used Python since first year, but it's like so damn short, dude. I normally use C++ because it's faster, but Python is so convenient. Like it, like list comprehension, even like set comprehensions, it just makes it so clean. Also, you can do like really wacky shit, like what is it? You can use frozen sets. I don't know any other language that lets you use frozen sets. They're whack. Okay. So yeah, sorry. So we have a gauge. We're going to apply n rotations to it, and for each rotation, we can turn it clockwise or counterclockwise. And we want it to be the case that after applying those n rotations, we end up right back at 0 where we started. So if you try and think of a clever clever solution to this, you might get stumped, and that's because there really is no clever solution. It's just a brute force. So you want to try, for every angle, try like turning it clockwise and counterclockwise. So that's going to give us, oh yeah, Vasar's like dictionary comprehensions. Yeah, dictionary comprehensions are awesome. And set comprehension. So tasty. So yeah, we're just going to use a brute force for this. So you could think, let's just like stop and think for a second. So we have n angles, and every angle has two possible states, right? It could be an angle that's clockwise or an angle that's counterclockwise. So that's 2 to the n possible states. So I need to effectively, I guess, write a brute force that'll try switching everything try putting everything in both of those states. And it turns out there's like a really clean and really efficient way of doing that. However, to show you that, I'm going to want to pull up my terminal so we can do some C++. Because this is a trick that's best used in C++ for maximal performance. So bear with me for like 1 second while I pull up my terminal. Here, while I pull up my terminal, I'll give you this wonderful copy of Sedgwick's algorithm textbook to feast your eyes on. There you go. Let me pull this up. Okay. Oh, this looks busted. That does not look correct. For some reason, OBS is kind of janky when showing Windows Terminal. I don't know why. I have a fix though. Let me fix it. Hey, there we go. So you guys should see my beautiful terminal. I'll scale it down a bit. Okay. Let's see, I'll move it here. And that's there, and that's here. Okay, we're good. So, I have a directory I like to do most of my stuff in, so I'll do this here. Let's see, let's copy, I've got like a light template that I like to use. Awesome. So now we're all like set up and ready to start coding. So we see in this question, so our first line contains, and actually, sorry, what am I doing jumping into the code? Before we dove into this, I want to actually dive into like the idea, like the core brute force idea. So sorry, let's go back here for a second. I'll even hide the book. Okay, so we said for every angle we wanted to try, yeah, like so we've got a gauge, and we've got a bunch of angles. Maybe I've got like 30 degrees, 20 degrees, 10 degrees. And for every angle, I could try it like clockwise or counterclockwise. So for every one of these, forgive this weird arrow. Okay. And now that means there's, there's n angles. There's 2 states for every angle. So there's like 2 to the n possible total states. And so we want to try each of these angles being clockwise and counterclockwise. So one way of thinking about that is, what if we said that an angle was clockwise if we had a 1 here, and it was like counterclockwise if we had a 0 here? Then I guess that's kind of cool, because then we could think about any state of our thing as being a binary string, right? So just to clarify that, if I had a binary string like 101, that'd be saying that let's do 30 clockwise, 20 counterclockwise, and 10 clockwise. Or another example would be if I did a 001, then maybe 30 is counterclockwise, 20 is counterclockwise, and 10 is clockwise. Now, why is it useful to think about it in this way? Well, if I want to try all combinations, then what I really want to try is all binary strings with n digits. And let's see what would that look like. So if I had 3 digits, that would look a lot like 000, 001, 010, 011, 100, 101. I think you guys probably see the pattern here. This is just like regular counting in binary. So the hacky thing that you can do is, since n is so small, actually just store this in like store like our state in a single integer where each bit represents whether like the ith bit in our integer represents whether the ith angle is clockwise. So I guess I'll give you a second to think about that. I've used this in an actual ICPC question once. It was like I forget the context of the problem, but it shows up enough that I wanted to cover it today. So with that in mind, we can actually look at the question now. So what is it? The structure was we read an n, which is the number of rotations, and then we read an n integers, where the ith integer is the ith rotation. Sure. And we print yes if it's possible to go back to 0, no if it's not. Okay. So let's read in n. Let's see an n. Nice. And then I'm going to go... So I'll make a vector. So a vector is sort of like a list in Python, if you're not a big C++ guy. I guess it's technically... It's not as nice as a Python list in that it can only store items of one type. But it's pretty handy still. So let's declare this. This pre-allocates n integers worth of memory. And I can go and read into my array. Now I've written all my values. So now I have to try all the different combinations. So here, let's see. So they said there was at most 15 things. So that's like what? That'll take 15 bits to represent. So your average, like a regular C++ int, has 32 bits to work with. So that's plenty for our use case. So what we're going to do is I'll make a thing. I'll call it like mask, let's say, right? I'll start it at 0. And I'm going to go, mask is less than... Here's the one, this is going to be the one weird part in all this code. Mask is less than 1 left shifted by n, mask plus plus. Now, why does that work? Because that seems bizarre. So if we think, so to clarify, this is what like a 1 is in binary, right? But if you do something like 1, like left shift by like 3, let's say, that like shifts 1 over 3 positions. So it adds like 3 zeros to the right. So if we have a 1 and we shift it over by n positions, what that does is it gives us the first number that's like not a pattern, not one of our binary strings we care about. Like it's like 1 digit too big, so to speak. Like if we're doing a 3-digit thing, then 1 left shifted by 3 would give us like 4 digits. And so this is the first value that we don't care about. Oh. Wait, can you not see? Wait. Let me... I should do this. This would make it a lot easier for you guys to see. Sorry. Thank you for mentioning that. Yeah. Where was I? Yeah, sorry. So the one weird thing I was talking about was this mask thing right here. So the rest is standard. Like we read in an integer n, read in our n like integers into our array, and then here this is our thing. We're going through. We've got a variable called mask, and it goes through all these different. Like effectively they're all the different subsets that we want to try. Like we're trying every different possible subset as the things we're going to turn clockwise. I feel like that's a horrible way of phrasing it, actually. Oh no, we're trying every possible binary string of length n. I feel like that's simpler. Okay, cool. So then the plan is, if the ith bit is set, then we add. So we'll go clockwise, which will be adding, let's say. And if the ith bit is not set, we'll go counterclockwise, which will make subtraction. So let's do that. So we're going to iterate through the bits. So there's n bits we care about. So go for, let's say, yeah, we can say I. I0, I is less than n, I plus plus. And I have to check if the ith bit is set in our mask. So to do that, we can say, so if I go, 1 left shifted by I, gives me like a 1 bit at the ith position. So now if I go mask and this, so think about this, right? Like, so if we have a 1 bit at the ith position, then this overall statement will only be non-zero if mask also has a 1 bit at the ith position. So all this statement here then is doing is it's checking to see if the ith bit is set. And then the thing we said was if the ith bit was set, then I'll go here. I'll make like let's make a variable called sum. And I'll say if it's set, then sum plus equals sorry. Yeah, sorry, then sum plus equals 8i. Oh, I don't really like how I've coded this. Let's do it like this. Here we go. Otherwise, we will do sum minus equals 8i. And then we want to see at the end of all this if we can get a sum that's 0. Because if at any point we get a sum that's 0, then we're like really happy. That means, hey, we got it to 0, we have a working solution. So we can actually just print yes and our early exit. Otherwise, if we make it to the end and we never manage to exit, then we're a bit sad, but we just print no. There we go. So let me make this a bit bigger actually, so you guys can see it all. Is that good? Let's see. Yeah, it looks good. Cool. So let's try running that on some test cases. So I'm going to save this, so you'll see I've got it locally. I normally make a few input files, so I'll go to the question and I'll say like, hey, copy this input, and this one. Wait, did I? Yeah, that's right. Cool. And this guy. Okay, so moment of truth. The answers we expect are, you can see it, right? Yeah, we expect to get a yes, no, yes. So let's see if we get that. So, so I'm gonna type R in my terminal, and that's gonna seem weird. So I alias R to run just /a.out. So if I go R arrow in, that runs my program with this first input. So give me an error because I didn't compile my program. Other weird thing I do, I compile my code by pressing F. F runs this like giant nasty looking compile statement. So if I go F, it compiles all my code, now I can run it. And cool, we get yes for the first one, no for the second one, no for the third one. I think we're supposed to get yes for the third one, right? Interesting. Wait, I don't think I understand this question. Because it says... Oh, wait. Let's look at this problem. Is there... Okay. So the other weird thing is this gauge is circular, right? So if we add... So we can effectively like delete any multiples of 360 out of our answer. Because if I go all the way around back to 0, that still counts as 0. So an easy way of deleting all multiples of 360 out of our answer is we say sum equals sum mod 360. Oh, but technically... Oh, I actually don't like that. Here, let's do... Yeah, absolute value of sum. So, in Python, sum mod 360 would be fine. C++ is kind of wonky, in that in C++, if you take the mod of a negative number, it doesn't necessarily become positive. It can still stay in the range. So here, for this problem, I think it's easiest to take the absolute value and then mod that. So this one's good, that one's good, that one's good. Nice, okay, it's looking good. So I have a macro where I can open my code and I press a key combination and it will copy my code to my clipboard. And now I just need to go here, go to submit on Codeforces. Now for some reason I'm not logged in, so let me log in. Bam, there we go. Nice, okay, sorry. Now we can submit. This should work. And boom, cool, we got full points. Accepted. Yeah, our code only took 31 milliseconds to run, which is really good. So that's nice. So now the best part, we go back here, and we're gonna say, we can green this out. Beautiful. Oh, this next problem is a classic. I think I've solved this problem so many times. Okay. So this is a graph problem. I find HackerRank actually has like hardly any good like entry like graph problems. Like they're all kind of hard if you haven't done graph problems before. But so in this problem, we're given a tree, which is a type of graph, and I guess I'll explain more in this section after. But so you're given a graph, and we're given a tree, and you have this weird thing where you can take any like even collection of nodes and cut them off the tree. It's like here, for example, I could take like, you guys can see my mouse, I think, right? You can take like this section on the right here, like 9, 10, 8, 6, and chop them off. Like you can say they chop it off here, or you can take 4 and 3 and chop it off. So I guess yeah, the idea is at any point we can chop off an even number of nodes. And so in this question, it's saying if I'm allowed to chop off an even number of nodes like this, what is like the maximum number of edges I can remove? And actually, wait, can I copy? Watch this. We're gonna do this. This is beautiful. Watch this. Hey, okay, look at that. We have an image. Okay, which I cannot scale. Interesting. Oh, there we go. Yeah. So the strategy we're going to explore is doing like effectively a depth first search, where we like start at one node and recursively like visit everything, but on the way back up. Oh yeah. Good call. Sorry, yeah. So what we effectively want to do is solve this using a depth first search. So what that does is it's just a recursive function. We can call it like DFS. And if I call DFS on like my top level node, it'll call DFS on all the children. And then the DFS there will call it DFS on its children, and so on and so on. And then what we can do is we could keep track of the sum of every subtree on the way back up on our DFS. So let's say when I'm running DFS on this node, this like child right here, it might say, all right, I have like no children, so the total number of nodes in my subtree, let's say, is 1. And then this guy, he has no children, right? So we'll say the total number of nodes in his subtree is also 1. But now if I step back a level, right? So if I'm looking at this node, he's already called DFS on both his children, and he knows that they sum to 1 plus 1 is 2. And he knows he himself is worth like 1 node, I guess let's say. So the total number of nodes in his subtree is 3. So when I say subtree, I mean like so we have some point we're calling DFS from originally. Subtree's like the tree like looks like this from a point. So it's like the tree, I guess, like facing away from the place we're calling from. So I guess like similarly here, if we step up again, if we have 4 here, then we see, hey, I have an even number of nodes, and I can chop it off. That's what matters. So we're effectively doing this DFS where whenever we see we have an even number of nodes, we increment a counter saying that we've chopped stuff off. So like similarly, if we keep running our thing, so we'd probably step back up here, we call DFS again. Let's say I call DFS here. Then I call it here again. I'd say I'm 1 node. I'd go up here, I'd say, hey, I'm 1 node and I have 1 as a child, so I'm 2 nodes. And say, hey, 2 is an even number, so we can chop here. Then I come back up here, and then I do the same thing again. And I'd end up returning actually 1 too many, because at the top of here I'd say, hey, I've got 4 nodes. But we don't care about chopping the last group, I guess, because it's already the last group. There's nothing to separate it from. There's no more. There's no other parent up here to cut it off from or anything. So DFS I find like makes a lot more sense when you code it too. So let's actually do that. So we're gonna pump up this terminal. Bam. Oh, actually no. Let's do this one in HackerRank. I lied. I do easy graph theory problems in on Python just because it's super clean. So let's go here. Delete. So I always recommend deleting the sample code they give you. It's normally not very good. First we look at the input format. I think it's pretty standard as far as things go. So the formatting is really weird for some reason, but the first line contains the number of nodes and the number of edges, and then the next number of edges, number of lines, that's a mouthful, gives us like pairs of things that are edges. So I guess, for example, here, if we look at the sample input, we have 10 nodes, we have 9 edges, and like our first edge is between like 2 and 1, so that's this edge right here. I have another edge between 3 and 1, and then it goes and it lists out the rest of the edges. Cool. So let's actually implement our thing then. So we're first going to read in, and I'll make sure I have chat open. First going to read in n&m equals map int input dot split. And I have to read in my graph, so I need a data structure to store the graph. I'm going to use something called an adjacency list. So the idea is I'm storing a list for each node that stores the, I guess like the labels for its neighbors, like what its neighbors are. So let's go empty list for I in range n. Is that right? So I'm going to do a bit of a hack here and make this in range n+1. So you'll notice that these are 1 indexed. So I'm just going to store my thing in a 1 indexed way, which means that I need to allocate like 1 more spot of memory. So I want to be able to index into this data structure at n. That's my goal there. So now let's go for this in range m. This is reading in my edges. I'd say uv equals map int input dot split. So those are the two node values of this particular edge. And then let's say g at u equals v, g of v equals u. So this is saying that v is in u's neighbors and that u is in v's neighbors. So then we can write a DFS that just like, I guess, calls on a node and looks through its neighbors and recursively like calls DFS on those children, and that continues recursively until we visited the entire tree. So let's write our DFS. Oh, sorry, and we're gonna need a global variable to keep track of the number of cuts we are able to make, so I'll make a variable up here. Now I'll make my DFS. Oh, another trick, so when we're writing a DFS, like the general logic for DFS is always like, so to run DFS on a node, you say, hey, what are my neighbors? And then once I know what my neighbors are, like call DFS on all my neighbors. But you notice that like, wait, can I make a new one? So we notice that if I start, let's say I start my DFS here, and then next step I go here, I want to run DFS on 8 because it's my child, but I don't want to run DFS on this guy because he's my parent. I've already run DFS on him. So what I can do is in my DFS, I'll always pass in my parent as well as the node I'm currently on, and then I can just avoid going back to my parent. So I could say like, if I go, what, for W, so this is a convention I use, I just say W is my next node. For W in my graph at X, I'll say if W isn't equal to P, so if W is not my parent, then that means like this must be one of my children. And I'll call DFS on my child, and I'll be the parent. And now I said, I guess here, that I wanted to keep track of, I guess, the sum of every subtree. So what I'll do here is I'll say, let's initialize here a sum to 1. We know it needs to be at least be 1, because the node by itself has sum 1. And then we can add the sum of our subtrees to our sum to get the sum of the total subtree that we're at the head of. And then it's pretty easy. We just go, well, if my sum is even, if my sum is even, that means my subtree has an even number of nodes, and that means I can cut it off. So then I can just do cut plus equals 1. And I think Python will complain if I try and access cut here without declaring it as a global, so I have to do this. Cool. And now the other thing to point out is, actually wait, sorry, I should call it first. So we can call our DFS on any node. It doesn't matter, so long as it's like one of the nodes given to us. I think they guarantee the nodes given to us go from exactly 1 to n, so we can just call 1. But we can equivalently call any other node and still get the correct answer. So let's call 1. It doesn't matter what value I pass in for the parent, because our starting node has no parent. And now, if we remember, our answer is going to be exactly 1 too big, because our answer effectively counts the groups rather than the cuts. So we need groups minus 1 will be the answer they expect. So let's go cuts minus equals 1, and then we should have our answer. So let's try running that guy, see if that works. And oh no, it's really not happy with me. Why is it not happy? So it says int object is not iterable. Interesting. So line 12. Let's see. So that's here, right here. So right now, g.x is an int. Ah, yeah. So here, look what we're doing. We're saying my graph's neighbors at u equals v. That doesn't really make sense. Because we see this should be a list of lists. So I really should be doing like my neighbor, like u's neighbors gets v. Like v gets appended to it. That's what we want, and same for you. So now if we do this, it should be slightly happier with us. Well, maybe not. Unsupported types for plus into none type. Why am I adding those? Wait, 9, 15. Cal plus equals 1. That's fine. Why is this mad? Let's see. Sure, that's fine. It shouldn't be mad because of my parent, I don't think. Here, let me just sanity check. It shouldn't matter, but I'm curious if this won't give me an error. Oh, I'm silly. So sorry. So you'll notice here that we add the... So I'm going to change this back to none. It doesn't matter. You'll notice here that we add the result of calling DFS on our child. And that's because I wanted each DFS call to return the sum of that subtree. So it's like, when you call DFS on a node, that DFS is responsible for getting the sum of, or I guess the total number of all nodes in that subtree, and it's allowed to make other calls to the children to accomplish that, which do the same thing. So let's try this. Yeah, you got it. Osama saw it in the chat. So cool, we can submit. And bada boom, bada bang, we got all AC. Nice. It's a classic problem. Classic hacker rank. Oh, this next one looks like fun. This next one's like kind of big brain, but like it's really fun. Although I think the problem statement's kind of poorly written. This problem statement is honestly so poorly written that I might just do it here in the text window. Okay. So let's say you've got a parking lot, okay? So you're given it, you got a parking lot, and someone's going to, ahead of time, give you a number n, just some like arbitrary integer n, and they're going to tell you that n's pretty small. N's like at most 30. And they're going to tell you that, hey, in our parking lot, we have, I believe it's 2n minus 2 spaces. So we can park like 2n minus 2 cars in our parking lot. Now the other thing they tell you is that we have 4 types of cars that can be parked in our parking lot. So let's call them like A, B, C, and D. So, for example, I could have car A parked in my parking lot, followed by B, followed by like maybe 2 cars of type C, followed by 2 cars of type B. Like you can really do like any combination of them, which is cool to start. So that's nice. But now we're going to impose another restriction, which is that we think our parking lot would be beautiful if it contained exactly n cars of the same make, so n cars of like the same type here, in a row. So that's to say, like, our parking lot is beautiful if it has n A's in a row, or n B's in a row, or n C's in a row, or n D's in a row. Now, there's a bunch of insights we should make about this. So, let's say I have my parking lot, right? And I designate some section that's going to have, so I mentioned this has to be exactly n in a row. So if I have n plus 1 cars in a row, that's no good. Let's say n is 3, and I have like A, B or something, that's like no good. We have to have exactly n in a row. So we have to do like A, B, C or something. That would be good. So yeah, so I was saying, so let's say we have some arbitrary region in the middle here. And yeah, let's continue with our example of n equals 3. We'd be happy if we had like these things all A, and then these immediately adjacent spots would have to be anything that's not A. So these could be like B, C, or D. Similarly, this one could be B, C, or D. And then we would call this a beautiful parking lot. And what's interesting to point out is that if I designated like this spot as my like section that I'm going to do my like big like long run of n things in, then it's not possible to fit another run of n things in this array. Why is that? Because our array is at most size 2n minus 2. And of course, n plus n equals 2n, which is bigger than 2n minus 2. So it's only possible to have like one I guess, like sequence of these n things in a row in our array, which is cool. So I don't know if I mentioned this earlier, but our actual end goal here is to output the total number of ways that we can like put cars in our parking lot. So we need to find like some way of like counting all of these things. So let's think on that some more. So there's effectively only like three cases, which are maybe just two cases depending on how you look at it, that we have to worry about. So let's say we have our parking lot, and let's say we anchor our, so we know that we had this idea of we want to have n things in a row, and that those n things in a row have to be somewhere in our parking lot. So let's have those n things in a row anchored right at the start of our parking lot. So this is of size n, and it's all going to be the same type. So we can make it like AA, AA. It would also be okay if it was like all B's or all C's. It just has to be all of the same type. So that's something we could do then, right? So we got our n things there, and then I have to have one special spot here that can't be, what am I saying? Yeah, sorry, it can't be the same type as this. So I guess normally we have 4 types to choose from, but for this guy we only have 3 types to choose from. And then these guys afterwards can be whatever we want. We don't really care. So then in this case in particular, let's count the number of total like beautiful parking lots we have. So number of beautiful parking lots where we anchor the sequential cars to the left. So consider that so the first thing we have to decide in this sort of thing is what our starting car is going to be for the run. So we could have 4 A's. I mean, I don't know why I'm saying 4. We could have n A's, n B's, n C's, or n D's. So because we have 4 car types, that means we've got 4 different ways that we could start this thing. And now, for each of like those 4 different things, we have 3 different choices we can make for this next spot, since it just has to be anything that's different, like any different car. And then finally, for these remaining things, for each one, for like every one of them, it can just be 4 different things. So these are all 4, 4 to the end. So then, I guess we could think of, all right, this total number then amounts to like 4 times 3 times 4 to the power of however many things we have here, and that should be, what is it? 2n minus 2 things is the total things in our array, minus n takes away this section, minus 1 takes away this guy. Yeah. So it's kind of gross. We could simplify this a bit. This will become what? 4 times 3 times 4 to the n minus 3. And then maybe I could add in this 1 4 here, so it becomes 3 times 4 to the n minus 2. So now it's pretty clean. And that would be the answer for this. And then we'll notice we could flip this logic on its head and say like, hey, what if we choose to end the parking lot with a sequence of n cars instead? Then it becomes like the same thing but in reverse. So like I'm going to have 4 different options at the end, 3 different options here, and then for each one of these ones, we'll have 4. So it's the exact same as this. So what we can actually just do is if we want to do both these cases, we can just take our answer from here and multiply it by 2. So we get like 2 times 3 times 4 to the n minus 2. Now, there's still one more case we have to deal with, which is, it could be the case that our sequence of cars is not at the start or the end, it's somewhere in the middle. If that's the case, then somewhere like in the middle, we're going to have n cars in a row, and then I'm going to have one special spot on the left that can only be 3 things, one special spot on the right that can only be 3 things. Our middle, of course, can be 4 different things, like the 4 different types. And on the outskirts here, it's like the same as before, where each one of these spots can be any of the 4, and we're fine with it. So the formula for this is going to be pretty similar, right? This will be 4 for this guy, times 3 squared, times 4 to the power of, what is this? I'm going to write out the whole thing again. So 2n minus 2 is our entire array, and I can subtract off n, subtract off 2 to get rid of these 3's, and yeah, that's what I'd be left with. So it'd be 4 times 3 squared times 4 to the, sorry, times 4 to the n minus 4. And then I can simplify that. So 3 squared times 4 to the n minus 3. And that's like a nice, pretty simple formula. So then all of this together would give us a final answer of 2 times 3 times 4 to the n minus 2 plus, what is this? 3 squared times 4 to the n minus 3, if we didn't mess up our math. So we should be able to do this in like 2 lines in Python. So let's give it a whirl. So you'll see the inputs here is just this number n. So I'm going to go to my terminal, and I'm going to remember to actually turn on my terminal. And nice. Now I can go here, and let's make a new file for this. So I'm just going to remove my existing guy. Let's go main.py. So I want to read an input. And so now we just want to use our math from before. So I'll pull up our math. It might be cut off, I think, for you, but I'm going to only have it up for a second. So we said, actually, no, I can make it display nice. Wait. Yeah, now you can see the math. Is this worth it? Maybe it's not worth it. It's not worth it. Okay, wait. I'm just going to type it in. Okay. So this will become 2 times 3 times power of 4 to the n minus 2 plus 3 times 3 times power of 4 to the n minus 3, and print our answer. Oh, I forgot we still had input files. Let's clear those up. Okay, now we need to copy the input from here. So they only give us one input, which is 3. Okay, there. So let's try that. So if I go Python main.py and I put in 3, it gives 33. Now we will notice that the correct answer is 24. So we are horribly overcounting somewhere. So let's figure out where. So the nice thing is 3 is really small, so it's really easy to debug. So this is just debugging our math rather than anything else. So let's open up our math. But let me just double check, make sure I typed it right first too. So what is it? 2, 3, 4 to the n minus 2. Right, is that right? 2, 3, 4 to the n minus 2. Yep. And what else? 3 squared, 4 to the n minus 3. Yep, that seems right. Okay, let's see where we messed up then. Okay, I'm gonna go back here. Okay, wait, so this is 4 options for this, and 3 for this guy, and it should be 4 for every one of these, correct? Yep. So let's see, 4 times 3, and it is 2n minus 2 things overall, correct? Correct. Let's check our math. So that becomes... yeah, 2n minus 2, minus the n, minus the 1. Okay, I can get behind that. So it becomes n minus 2, minus 1, so n minus 3. And then if we add 1 and 4, that becomes n minus 2, so 3 times... Oh! No, I have that. 3 times 4 times n minus 2. That's good. Similarly, I have to multiply by 2 here. Yep. That's fine. And for this case here, it is, what? Yeah, 4 times 3 squared times, yep, 2n minus 2. We take away the n for the middle, take away the 2 for these side guys, leaves me with n minus 4. This becomes, yeah, 3 squared times n minus 3. So this seems good, so I don't see my error immediately, so this is going to be more fun to debug. Oh yeah, so one thing you can know for any of our MCP live streams, they all get posted after too. Yeah, so I know that these events can get kind of long. Like I know this one's like 2 hours, so don't feel pressured to stay like the 2 whole hours or anything. Like everything gets posted after, so it's easy. Also, I'll say too, it's kind of fun for ICPC tryouts. the plan is to have the problem authors like Daniel and Mikhail like go through the questions after, and so that'll also get recorded and like put up. So this will be cool to view. I don't think we did that last year, so it'll be cool to do that this year. Okay, so yeah, let's look at. Let me sanity check because this case is so small. N equals 3 that we can effectively draw it out. So if n equals 3, then my array size, which is 2n minus 2, is equal to 4, which is pretty small. So effectively I've got this case. So the case where it's at the start, the case where it's at the end, and then I don't even have the case where it's in the middle because it's impossible to fit it in the middle here. So let's see, for each of these side cases, I should get, what, 4 times 3 things. Because I'll have 4 different values here, like I can go like AAA, BBB, CCC, or DDD, yes. And then for each one of those, I'll have 3 remaining options that I can choose from. So it should just be 12 for this, and 12 for this. And that should add up to 24, which is our correct answer, right? Okay, that makes sense. And now we're not getting that for some reason. Now our logic, though, was we said we could just do... it's here, right? 2 times 3 times 4 to the n minus 2. Let's see. 2 times 3 times 4 to the n minus 2. So, let's see. 4 to the n minus 2 here will be 4 to the 1. So 2 times 3 times 4. So this is actually correct. This part is giving me the correct answer for this part. So the part that's messing us up then is probably this thing right here. I probably messed up this. So let's see why. So we claimed that we could do 3 squared times 4 to the n minus 3 here. That's what we said. 3 squared times 4 to the n minus 3. Oh, I see. This is just yeah. I think we may have to have a requirement here, like we only do this, like, if n is greater than 3. Because if n is exactly 3, then we don't have actually anything that we're setting as 4. It's effectively just doing, like, how do you even say that? Like 2 3s and then everything else is just, like, free. It's kind of sketchy. Oh, also I didn't consider the positions. Okay, so this is run on like 2 counts. So yeah, what we should do. There's 2 things we have to fix here. So first, we only add this section to our answer if n is greater than 3. Because n has to be at least 3 for us to fit our thing, I believe. Okay. Okay, wait, I have to go answer plus equals this. The other thing was, so we mentioned earlier that there's, so these ones are kind of boring that they're like fixed to the end, right? But for the guy in the middle is really interesting in that we can move it around. So there's like a bunch of different positions. Like I could like slide this guy around to, like this guy from here to here. I could slide him left or I could slide him right. So the number of positions, I have to make sure I do this right. I think it should be, like, what is it? The total length. So yeah, the good way of thinking about this is you think like, well, let's say I had, just for fun, I had something of size like W, right? And I was sliding around a tile of size 1 on it, right? Then there'd be like W different positions that I could place that tile of size 1 in. But if I had a thing of size W and a tile of size like 2 that I was sliding around on it, there'd only be W minus 1 positions it could be in. So now extrapolating this to its conclusion, if I had something of width W with a tile of size N on it, there would be there'd be W minus N plus 1 different positions it could be in. But then, if we add in the restriction that it can't be in the rightmost position, because that's this case right here, and it can't be in the leftmost position, because it's in this case right here, then we only have like W minus N minus 1 places it can be in, and we happen to know that, like w here, if that's the width of our array, well, our width of our array is 2n minus 2. So then we can, this entire question is just math, I must confess. Then the number of positions we can put this thing in is 2n minus n, sorry, let's not get confused, 2n minus 2 minus n minus 1, which is n minus 3 positions. Oh, now this actually makes sense, right? So, you know how before I said we needed a special case for n bigger than 3? That's actually handled by this. Because if n was 3, that would mean that there's exactly 0 positions that we could place our like sliding tile in. So, instead of having an if statement in my code, I can just go, it's going to be a beautiful one-liner. Plus n minus 3 times this. Also, it's been bugging me. I'm going to replace these 3's with a 9. There we go. Okay, so this works. It's like super beautiful. Let's try. So that. So correct answer on the sample. Let's try submitting. Oh, wow. This contest had a lot of questions. It was called, let's see. This is problem I, parking lot. Okay. So let's go here. Problem I, parking lot. Paste in our code. It's a very short program. If you're really ballsy, you can just code directly into the submission window, but I normally don't do that. Alright, we submit this guy. Oh, wait. So, you'll notice I just submitted that code as C++, so that's not right. This is Python code, so let's submit it as Python. In fact, let's submit it as PyPy, because for those of you who don't know, PyPy is pretty much, it's very, very similar to Python, except it uses like a just-in-time compiler that's like, I don't know. So it'll run your Python code like just the same, but it will run it maybe like 10 to 100 times faster. So like pretty much, if you ever have the option, you should also always just run your code using PyPy instead of Python. That's like the general like rule of thumb. But anyways, I digress. Let's paste our code in here, submit it, see if we did the second part correctly, and boom, bada bang. That is a clean solution. So small. Okay, now you might have noticed that I'm not going to put green on this yet. I have binary exponentiation next to this, and I never talked about that. So in our code, we rely on being able to raise an integer to a high power. I mean, this honestly isn't that high. Binary exponentiation, which is this technique I'm going to teach you, is totally overkill. Like, I could write a for loop or something that would do this power for me, like just as equivalently, and that'd be fine. But we're going to look at a way that you can raise things to a very high power, like very efficiently. Yeah. And sorry, I should mention too, I think a lot of people don't know this. So if you're in Python, am I showing my terminal? I am. Alright, beautiful. So if you're in Python, and you open up your terminal, you can go like power of like any number, right? To another number, and it will give it to you as a nice integer. Oh, that's way too big, right? I forgot that these actually grow like stupidly fast. Let's do a small number to like a big power. What am I doing? Okay, like this? Yeah. So you can see it gives it to you as an integer, which is really nice. Now, if you're in C++, that's actually not the case. Like if you call stdpow, which is like, I can even pull it up. If you call stdpow, which is like the C++ standard like power function, you'll notice that it actually doesn't return an integer. It returns a float. And there isn't a version of it that returns an integer. You see all of these return like doubles, floats, or long doubles. So if you want to raise an integer to a power in C++, you either have to write a for loop. Like, let's say I want to multiply a to the power of b, like some number of times. Like I want to go, if I want to go a to the power of 6, I could write a for loop in my C++ and go like a times a times a times a times a times a 6 times. So that would take like time proportional to the power I'm raising it to. So if I'm computing, wait, I'll make this a 6, clearly. If I'm doing like a to the b, where b is like some number, then using this method takes like o to the b time to compute, which is pretty slow. Now, it turns out that there's a really clever trick we can use to raise an integer to the power of another integer in a O log b time, which is really clever. So the idea stems from the fact that, let's say we're computing something like, oh, I don't know, a to the 13. Or even, actually, I don't know why, I really like using x. It makes me really happy when I use x instead of a. Okay, so I'm computing x to the 13. The naive way of doing it, as we mentioned, is to multiply x 13 times, which is pretty slow. But maybe a better way is to think that 13 has a binary representation, right? We can think of 13 as what? 8. God, can I do this? Yeah, 8 plus 4 plus 0 plus 1. Sorry, yeah. 8 plus 4 plus 1 gives us 13. Did I do this right? 5. Yeah, sorry, that's correct. So this is kind of interesting, and it may not be clear why this is interesting, but have you considered that if we ever have x to the a plus b, that's the same as x to the a times x to the b. And wait, if we have a number 13 that can be represented by in a binary representation like this, that means that 13 can be written as like 2 to the 0 plus 2 to the 2 plus 2 to the 3. And that means, in the context of this thing here, here's where it gets big brain, is that we can write x to the 13 as x to, what am I saying? Oh, sorry. X to the 8 times x to the 4 times x to the 1. And then so the trick is, for any number b that we want to raise something to the power 2, we can find the binary representation of b. We can figure out like which of these powers of our base, like x, we need. And then we can just compute like x1, x1, x2, all the way up to, I don't know. Actually, wait, what would it be? It'd be I don't have a good way of saying it. It'd be like the biggest power of 2 underneath our number. I'll just say like, I don't know, x16 is an example. And then, what am I saying? So we compute these, of which there'd be log n of them. Sorry, log b of them, I should say. And then you just like multiply our answer by the relevant ones. So you can do this in like, or always like log b time. So let's try and actually code that up. So in practice, what that would look like. So let's copy a template here first. So go here. There we go. So I'm going to make a special thing called bind pow, which is going to compute a to the b. Make sure I've got chat open too. And so consider that like x to the 2 to the I, we want to multiply by x to the 2 to the I if the ith bit is set in our number. Like for example, consider like in 13, like this, like let's call this like the 0th bit. Oh wait, I need my pen. Sorry. Let's call this like the 0th bit, the 1th bit, like the 2th bit. So notice like the 2th bit is set here, and then correspondingly, like 2 to the x to the 2 to the power of 2 is like something that we multiply by. So all we have to do, I guess, is iterate through the bits in B, and whenever that bit is set, we'll multiply, let's see, it's a mouthful to say, we'll multiply x to the 2 to the I, we'll multiply, x to the 2 to the I by our answer, and store that as our new answer. And we can always compute efficiently like x to the 2 to the I, since it's just this, it can be computed as x to the 2 to the I minus 1 times x to the 2 to the I minus 1. So this might make some more sense in code. So let's do, first let's iterate through all the bits. Let's go for int I, oh actually I can even, yeah, that'll work. So I only care about set bits in B, so I'm actually just going to like shift B to the right until we have no more B. So let's go will I have b? So b is not 0. B right shift equals 1. And then every iteration, I say if b is set. So this is a sneaky way to see if your first bit is set. You just AND it with 1. So this will tell you if your number is odd, because a number is odd if the first bit is set. So instead of doing that like mod 2 equals check that people tend to do, you can just do this, which is faster too. Anyways, so if our ith bit is set, then I'll do my answer too. So then my answer is going to become my answer multiplied by my current power of x. So my trick here, which is kind of sneaky, so consider that for the first, I guess I'll go back to doing using a's. In my, like when I'm looking at like the first thing, right? If this bit is set, then I'll multiply by like x, right? And then in my next one, I multiply by like that value squared, effectively, if it was, like if I had like an x to the 2 in here, which I don't, but if I did, I multiply by x squared. So what I'm going to do is on my ith iteration, so to speak, I want this a in my code, I guess. So a in my code there to be equal to the original, how should I denote this? Like I'm going to do a is equal to like its previous a just times a, like that's as simple as that. But yeah, sorry, I'm just gonna use some gross notation. Let's just do it like this. So a on the ith iteration, I'm gonna write this out super formally, should be equal to the original a raised to the power of 2 to the I. That's the golden thing. So that means on my first iteration, like 2 to the 0 is 1. So that one means ai equals in my a original. And then I can compute a at I plus 1 is just a at I times 8i. So at the end of my loop, I'm just going to do that. That's the one confusing part. So tell me if you guys have any questions with that. I'm just going to go a equals a times a. So then this property, this invariant, I guess. Oh, sorry. Will hold. Let me turn on my terminal at the end of every iteration. So yeah, say that. Sorry, outside of my terminal. So I'll quickly go over that. So I'm iterating through every bit in B that's set. If it is set, I multiply my answer by my current a value, and then I square my a value. So I'm just going through all the squares of a. So it'd be like to the first power, to the second power, to the fourth power, to the eighth power. I'm effectively doing that. And then I should just be able to return the result. And that should just work if things are good. Now one thing to watch out for here, it's really easy for this to overflow. So most of the time if you're doing something like this, I recommend using longs instead of integers. So a long is a 64-bit integer in C++, whereas your regular ints are only 32 bits. So I think a long will get you can store values up to around like 10 to the 18, whereas a regular int will cap out around 10 to the 9. So sorry, let's replace this with long. Bam, just like that. Okay, well I have B. Just making sure this looks good. Curly braces are overrated. Yeah, okay. And now we're effectively just going to copy our code from before. We could even open it up. Here. Okay, so we want n, put in n, and compute what? Answer equals okay, 2 times 3 plus line pow of 4 to the n minus 2 plus n minus 3 times 9 times line pow of 4 to the n minus 3. Yeah, I'll even like space this out. You know, you don't need parentheses here, but I feel like for peace of mind, I want parentheses here. It just lets me sleep at night, you know? Okay. Yeah, that seems right. Yep, okay. So let's try compiling that. Our compiler will inevitably get mad at us because we never printed it. So let's print it. Okay, so that's a bit too small. Let's see if we can figure out what our bug is. Okay, so actually, this is a fun thing to show. So if you're debugging C++ programs, there's a handy utility called GDB that lets you just like run the debugger on your code. So let's do GDB a.out. Let's break in main /n. Cool. So now I'm inside my program, and I'm able to call the functions and everything. So I can go like, I don't know, if I can print like the value of n, or I can call like binary power or something. Like I could do like 1 to the power of 2, which would be 1, right? Yeah, 1 to the power of anything should be that. Cool. So in our code, let's try some powers of 4, make sure that works. So 4 to the 1 worked, 4 to the 2 works. Oh, this is working so far. Okay. So specifically in this one, if I remember correctly, if I pull up our, let me turn off my terminal for a second. If I pull up our thing here, we did what? 2 times 3 times 4 to the n-2, right? So let's try that. So binary power, so n-2 is 1. That makes sense. So 2 times 3 times binary power 4 to the n-2. I forgot print. It's 24. That's exactly correct. That's good. So I guess the problem then is with the second statement. So what awful thing do we do in our second statement? Let's look. So if you press L in GDB, it'll show you here, right? It'll show you your code. So here I pressed L and it says, okay, you've got this plus what, n times 3. Oh, here, how about this? This is probably what we don't handle, right? What is binary pow 4 to the n-3? Oh my god, I forgot things. Okay, right. No, that's right, that's 1. Wait, why is this not returning the right answer? This should return 24, right? Because wait, if I print this, that gives me 10. Oh, wait, what? That should be 24. Oh, haha! Do you see my bug? Go figure. Okay, wait. That's a classic error. Okay, here we go. Okay, I'm happy. Okay. Okay, copied that. Let's try submitting this guy. Oh, sorry, I turned off my terminal there for a second. What the error ended up being, if you're curious, was right here. I had a plus sign. Should have had a multiplication sign. There's plenty of those errors. It's kind of funny when you're doing ICPC at regionals. It's often helpful when one person is coding. You sometimes have a second person acting as like almost like a human syntax machine. They just like stand there and go like, oh, like extra parenthesis, like, oh, did you mean, you probably meant to do this, right? They can help you find like little logical errors like that too. It's very handy. Cool. So let's open this then, copy it, exit my terminal, go back to here, and we should be able to submit. So let's see, where were we? Parking lot, submit. We have to make sure we change our code to C++, and we can submit. Wrong answer, that makes me sad. Oh, I hope, if this needs big integers, then I'll just give up. Big integers really suck. Let's see. So in Code Forces, if you get something wrong, you can just open it up here and scroll down and see what you messed up. Yeah, so it looks like I overflow. So in C++, if it doesn't fit, the value will overflow. So you can see here I just overflowed. It's odd though, it's not that big. This is only like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is only 10 integers. This really shouldn't overflow. So let's figure out why it's overflowing. Oh, I know why. Sorry, it's very easy. So let's go back to our code. So you'll notice in our code, we declared we declared answer as an integer. So that means that if our answer is too big to fit in an integer, it just like wraps around, and you get like a weird negative result. So we have to declare this to be a long long. And now our code should work. Let's see. Unless we messed up somewhere else. So we'll go back here. Let's submit again. yada yada. There we go. Working on paste it. Go. And moments of truth. Yeah. That is AC. We are happy. Ooh, I see a comment in the chat. Sidar and Takari try signed. Yeah, I almost like to do the opposite. Like, yeah, long n. Honestly, long n will be overkill. So, in C++, this is actually a good lesson too. Because C++ does some sketchy things. So, in C++, if you multiply like an int by a long, the result will be a long. So that's like okay. But the one thing that can totally kill you, and this killed me when I was starting out, like, and I had no idea what the problem was. In C++, if you multiply like an unsigned integer by a signed integer, I think the default behavior is it actually converts to unsigned. Not convert to signed, but convert to unsigned, which is so wacky. I haven't even done that in so long. But anyways, just like rule of thumb, basically never work with a combination of signed and unsigned like variables. You're just gonna shoot yourself in the foot. I honestly I'll work in signed unless I absolutely have to work in unsigned. Yeah, so that's good. So let's go back here. And this is lovely. We can say, we got this guy. Oh, I was looking forward to, oh wait, another comment, wait. In Python automate stuff? Yeah, honestly, Python is so nice. Dude, I love Python. Like in Python behaves like how a computer program should behave. In Python, if I open up my terminal and I go like, let's say like 5 mod 3 or something, it gives me 5 mod 3. And if I go like, let's say -5 mod 3, it gives me 1, which makes sense. But if I go in C++, like let's say I run my previous program, right? And I put in a breakpoint so I can execute code. Now I can run like statements and stuff. So if I do 5 mod 3, right? It's 2. It makes sense. But if I do -5 mod 3, look at this. Look, get ready for this. Wait. It's -2. It's negative. It's bonkers. If you want to get this accurately, if you want like a real mod, you have to do like +3. No, not even. You have to do like -5 mod 3 +3. Yeah, you have to do that. It's gross. That's why C++ modulo is bonkers. You shouldn't use it. I mean, you have to use it, I guess, at the end of the day, but like, you have to be aware that it's so easy to kill, just like shoot yourself in the foot with it. Okay. So next program, this is kind of fun. This is unusual for our club. We normally do our stuff on HackerRank or Codeforces, but this problem is actually on Spodge, which is like another entirely different judge. So let's see. The context for this one was, let me see. Okay, so we're given like t, which is the number of test cases, and then we're given a bunch of numbers n, and I think we want to find all numbers less than, is less than or equal to or less than? Let's see. Oh yeah, sorry, it's less than or equal to, so not greater than. So if you say all numbers not greater than n, that's the exact same as saying all numbers like less than or equal to n, that these guys are afraid of. And it says here that these guys, like Changu and Mangu, are afraid of, they're afraid of prime numbers. And let's see, there's one variation, it's like, they're afraid of this. Wait, let me see. They're afraid of all the prime numbers. Okay. Okay, so if it has a 0 in it, then they love it. Oh, okay. So they're afraid of all prime numbers, where if you strip off the digits from the left, they remain prime all the way down. So, oh, yeah, so very good point. Right now, there's a giant terminal blocking my screen, so you guys can see, like, squat all. So, if I delete this, now you guys can actually see. I should zoom in a bit, too. Okay. That's better. Okay, beautiful, yeah. So, sorry. So, there's two guys, Changu and Mangu, and they're afraid of prime numbers. Now, they're only afraid of a very special type of prime number. So, if the prime number has a 0 in it, they're not afraid of it at all. They're like, who cares? They're only afraid of prime numbers where the original number is prime, and if you strip off the digits from the left, it remains prime. So, for example, this number here, it's prime, and it starts with a 4. If we take off the 4, it's still a prime number. If we take off the 6, it's still a prime number. Take off the 3, still a prime number, and so on all the way down. So we want to count the number of numbers, it's a mouthful, that are like that and that are less than or equal to n. So I think a good way of approaching this is, so first we want to see how big n can be. So n can only be 10 to the 6. So it's totally okay to do something in time that's like linear to 10 to the 6. That's like totally okay. We could probably even do n log n. And I think we're actually probably going to do exactly that. But that's like foreshadowing. So now, let's say I'm looking at a particular number. How can I find out if Chungu and Mungu are afraid of that particular number? Well, I guess first I can check and see if it has a 0 in it. Because if it has a 0 in it, then they're not afraid of it. So that's good to know. But if it doesn't have a 0, then I guess what I want to do is like see if the original number is prime, then like subtract off the biggest digit, and then see if the next number is prime, subtract off, and so on all the way down. Now, assuming I have some like super fast like way, let's say I have some super fast like constant time way of checking to see if something's prime, then my runtime to check and see if a particular number is something they're afraid of would just be proportional to the length of the number. Now, the number of digits in a number grows like logarithmically, so that's like pretty small. So it takes, I guess, like log n time then to check a particular number and see if they'd be afraid of it. And if we have n numbers we need to check, that means it would take sorry, I just realized something. Sorry, if there are n numbers, that means we'll take n log n. Now there's one other like kind of really weird gotcha here, in that they don't just ask us like one query, they can ask us up to 10 to the 5 queries. So what I think I'll do is I think I'll pre-compute the answer for every query. So I'll store something that's like the number of like fearful numbers up to this point, and then I can just answer their queries by querying that. Now, so we kind of have an idea for a solution then, I guess. But it's all reliant on being able to efficiently tell, like in O1 time, whether or not a number is prime. And now, that's not necessarily like that easy to do. Like if you just give me a number, I can't tell you like instantly, hey, this is prime or this is not prime. Probably the fastest thing I could do, like if you give me some number like n, the fastest thing I could do is iterate from like 1 to square root of n and see if n has any divisors. And if it doesn't have any divisors, then I can say it's prime. But that takes like root n time, which is pretty slow. Like if we try to use that in our solution here, we time out. But luckily, it just so happens, what we can do is we can pre-compute all the primes. And then we can pre-compute all the times, which will take, we'll prove this later. I mean, I haven't even told you our approach yet, but we have some like magical algorithm that'll pre-compute the primes in n log n time, and then once we have that, we can check if something's prime in like constants like O1 time. So the trick we're going to use to pre-compute if numbers are prime is something called the sieve of Arrhenius. So what it's going to be, the idea is something like this. So let's pretend we have an array. And let's say, just for fun, I know this is heresy, so forgive me, but I'm going to label the first element 1. I know it's like basically a crime, but I'm going to do that. And so let's number some of these, like 1, 2, 3, yada yada yada, all the way down for a bit. So I guess right away we know, just like by definitions, one's not prime. Now 2 is a prime number. Now, an interesting thought is 2 is a prime number. Any multiple of a prime number is not a prime number. So what if, after I see 2 is a prime number, I go and I cross off every, like let's say I've got some data structure storing whether something's prime or not, and at the start I say everything's prime. But then whenever I encounter a prime number like 2, I say, hey, let's cross off every multiple of 2 in our data structure and say it's not prime. So let's go and say, well, 4 is not prime, 6 is not prime, 8's not prime, 10's not prime, 12 is not prime. All the way down through our entire array. And then let's go and let's say we hit 3, and we'll say, well, 3, it seems like it's prime. So that's prime. So let's jump like every multiple of 3 and turn it off. So I've already turned off 6, so that doesn't do anything. I haven't turned off 9, so let's turn that off. I can turn off 12. And so on, and I can keep doing this. So like when I hit 5, I do every multiple of 5. When I hit 7, I do every multiple of 7, and I continue all the way down. And then at the end, I'll have this array where, like, either something is like prime or not prime. Like I have to have some convention. I think I normally do, if it's 0, it's not prime. So sorry, if it's 0, it's prime, and if it's 1, it's not prime. Because then I don't have to set the memory initially or anything. Oh, we have a comment in the chat. MCP doing very great work. Oh, thank you so much. Very glad you feel that way. I love doing this sort of thing. Tell your friends about tryouts. Sorry. So this is, I really, really like this algorithm because this seems like it'd be so slow, right? So consider like when we looked at 2, right? We turned off every second element. So that means we had to look at like roughly like n over 2 elements and turn them off. And then for 3, we had to look at, I guess, like n over 3 elements and then like turn them off. And then for 5, we had to look at like roughly like n over 5 elements, and so on and so on. And so this seems like it'd be a lot of work, like, right? Like we're doing like something that seems like almost proportional to linear work every time. However, so this is like pretty wild. This honestly knocked my socks off when I first heard it. Let's say we factor out this n, right? So this series here, if we factor out the n, it's equal to this, like 1 over 2 plus 1 over 3 plus 1 over 5 plus 1 over 7 and so on. And this is less than, so this is like strictly less work than doing this, which is even more work, which is 1/2 plus 1 over 3 plus 1 over 4, so doing like 1 over every number. So this is like an upper bound on our runtime. Maybe I didn't really explain that fully. I should. So the total number of work we do in this algorithm is like roughly proportional to the number of elements we looked at. And so if we can kind of like get a sense of how many elements we look at, we can get a sense of how fast our algorithm is. So here we see like we looked at like n over 2 plus n over 3 plus n over 5 plus n over 7 elements, and so on and so on. And so we could factor out that n, and we get this. And then we say, hey, that's like strictly less than this. So this is like an upper bound on our runtime then. And it turns out, if you, I don't even know the proof off the top of my head for this, but if you look this up online, this series here actually if you sum up like n terms of the series, so you sum up all the way to like 1 over n, this actually like converges to log, like order log n, something of size like order log n. So why that matters for us is that means our overall runtime for this algorithm becomes like n log n. Actually, I said this converges to order log n. I think this actually converges to like exactly log n. It's actually wild. I think it's in. It's also in. Wait, I have the perfect photo for this. It's actually in your Sedgwick. It's in your Sedgwick textbook, right here. So if you have this textbook, you can actually go and look up this fact. But so that's really cool. So we could use an approach like this. It seems fairly simple to implement. We just do like multiples of the primes, and we can guarantee it'll run in n log n, and it will give us a big array that allows us to check if numbers are prime in O1 time. So now all that's really left is for us to code it. So let's do it. Oh yeah, also, you probably noticed that weird thing too. Like I do n LGN, like there's no O, and you're probably like, why the hell doesn't he have like an O? There's a popular computer science notation where instead of writing a log base 2 of a number, like log base 2 of x, you just say LG of x, and it means the same thing. So it doesn't really matter because it's big O. Like in big O, this is like totally the same as saying this, because constant factors don't matter. But just as a convention, I pretty much always write like my base 2 log, just because I'm so used to it now. Alright, so let's code this bad boy. So yeah, first thing is pre-computing all the primes. So let's go. I'm gonna clear my directory. Oh, I didn't clear it. Why? Oh, because I didn't do star. Okay, true. So by the way, you should never type this command into your terminal. Don't copy me. It's a very bad choice. You will delete your file system. Okay. So let's copy a template. Put it in here. Okay. So we need a big array to hold. Like what I'm gonna do is effectively gonna be a Boolean array. Like I say int, but normally in C++ if you use a Boolean like this, it'll actually be using an int anyways under the hood to store it. So I'm just gonna use an int in the first place to begin with, just because I love ints. And the other question is, how big do we have to make this? So we have to make this at least as big as the biggest prime that we have to check. And if we look in here, the biggest prime we'd have to check is n. And n is at most 10 to the 6. So I'm just going to make a top level define. Oh, And oh, thank you for that. I need to turn my terminal. Yes, sorry. So yeah, so all I was saying was we need like a big array at the top that's going to hold whether or not things are prime. And so let's make a sum n, which is the, I guess I'm going to make it a bit larger than the possible prime, just to give myself a little breathing room. So 10 to the 6 was the biggest, so I also like add like some random integer. 10 to the 6 plus 5, just to give myself a little breathing room. Because if you make it too close, like if I make it exactly 10 to this, and it turns out I'm off by 1 or something, then like you might have to chase down an off by 1 error, which is always scary. So I give myself a bit of slack always if I can. So, sorry, I allocate my array of size n, and now let's write some code to like pre-compute primes. So, you know, I call this pre-compute primes. A real better name is sieve, because it's the sieve of Arithmenius. Okay, so right away, I guess we said that, I guess 0 is definitely not prime. So we can say, if it's marked, that means it's not prime. So that's 0 is not prime, 1's not prime. What else? What am I saying? Oh yeah. And now we can start our algorithm in earnest. Sorry. So now we're gonna go for int I equals 2. Well, I is less than n, I plus plus. So this is iterating through the elements in my vector, or in my big array, I should say. And if I see that it's not p at I, that means it's a prime number. So just for half a second going back to our drawing board we had set up. So remember here that we marked off some things and said like, hey, you're not a prime. So if something is marked off like this, that's equivalent to it being set as a 1 in our array. And so we only want to like run our fancy like skip and turn everything off algorithm, like if we can count our prime. So then back in my code I say, like if not p at I, that means I is a prime. Which means we want to skip and turn everything off. So the naive way of doing this is you go like, oh, let's make sure I do this right. For int j equals I, and then you go, yeah, so we can start I plus I, and then go, well, j is less than n, j plus equals I, so we're jumping by I, we're just like skipping by that length. So like if I was 2, for example, we'd be doing like multiples of 2. If I is 3, we'd be doing multiples of 3. That's the general idea. And then we're just saying all of these can't be prime, so we're turning it off. We're saying p at j equals 1, so j is not prime. And that's actually the full algorithm, pretty much. I think there is some optimizations we can make, though. Let me just think. I think there's a thing you can do. Yeah, so this is kind of big brain. I'm pretty sure we can start with this as j equals I times I instead of I plus I. So I think the intuition here is let's say we had a multiple of I that was less than I. So let's say I'm considering like I equals 5 or something, and we had like 5 times 3, then that would have already been turned off by when we turned off the multiples of 3. Yeah, so we can start at I times I. So think about that for a second, because that's like very weird, honestly. But that's like a very small like optimization. It won't affect our overall runtime much. And I think this should work, right? Like we check every prime and we go all the way down. Yep, that should be fine, honestly. Okay, cool. So now we've got like a magical thing that'll tell us if our numbers are prime or not. So that took a little while, so let's refresh ourselves on like the actual question. So now that we have that, the idea was we wanted to see like for all the numbers if they're like a fearful number or not. And a number was fearful. It's not fearful if it has a 0. It is fearful if it's prime and all of its like stripped versions are prime. I'm trying to think. This stripped thing is going to be kind of annoying to implement. Oh, well, let's figure it out. So it'll be something like... Sorry. So right now I want to go through and say, oh, actually, you know what's a... Oh, wait, sorry, I'll mention that later. What I'm thinking, I want to keep up like some like partial sums data structure to keep track of the number of fearful things up to a certain point, which we'll use later. But we don't need to worry about that now. Right now we just want to worry about, we're going to iterate through all the numbers and see if they're fearful or not. So let's go like for int, what? I equals 2. Yeah. Let's go. It doesn't really matter. I just don't want to have to handle the edge cases. I know 0 and 1 aren't fearful, and I don't want to have to handle the edge cases for them. So I'll just start with 2. So go for int I equals 2, I is less than n, I plus plus, and then, actually no, maybe I'll start with this. So at the end of the day, it'd be cool to have some data structure that'll tell me the number of fearful things up to a certain point. Sorry, wait. Did I bug my code? Oh, sorry. I may have deleted my code. Forgive me. Okay, let me just do this. Forgive me. There we go. Sorry. Things are fixed. Okay, sorry. So, I think it'd be nice to have some data structure. I'm going to call it f. It's just going to be an array. And it's going to store the number of, like f at I is going to store the number of fearful numbers up to the point I. So then I could have something like for int I equals 0, I is less than n, I plus plus, f at I is equal to f at I minus 1. So the number of fearful things up to and including I is equal to the up number of fearful things before me plus 1 if I'm fearful. So plus, I could just make a thing that, like a fearful function that returns true or false. And so the cool thing is, if you add a like true plus 1 in C++, this will give you 2. So that's kind of cool. So I can just go like bool fearful takes in, let's say int x. Cool. So now this is the one annoying part of the problem. So I have to do 3 things. First I have to do check if there's a 0. Then I have to, I guess it's 2 things. Then like see if everything is prime. And by everything I mean like all the chopped off versions. So let's see, what's the easiest way to check if it's a 0? Oh yeah, this is pretty easy. So I can use if you guys were watching earlier in the stream, when we did the binary power thing, we did a thing where we shifted the bits, and every time we check the bit, we can do something sort of similar here, except we'll work with decimal digits instead of bits. So we'll do like, x is not 0, x divide equals 10. So what that's going to do is it's going to delete the bottommost digit. And then if at any point, if we have that x and... Sorry, if it's not the case, if it's at some point it's not the case that we have x and 1, that means the bit's not set. And if ever the bit's not set, but we still have a non-zero x, that means we have a 0 bit. So then I can just return false. That's sort of confusing, but it's like, I'll draw something here to make that make sense. It's like, so if you think of the binary representation, right? You could think of there being an arbitrary number of zeros to the left, then you've got your number. And so, if I go through this normally, right? Sorry, I'm thinking binary. We should be thinking decimal, but it's the same idea. So I've got some arbitrary zeros on the left. I've got my arbitrary decimal digits. This is a very large number. So you could think, in my algorithm here for fearful, I first start, I look at 2, and I say, well, oh yeah, wait, sorry. It should be if x mod 10. If not, x mod 10. No, that should work. Okay, sorry. So when we look at 2 here, right? We'll say, so x mod 10 will delete everything that's bigger than 10. That's like a multiple of 10, so everything except for 2. So give me just this 2. And, yeah. So if I have a value here, I can just do this. So if I have a value, no, I messed up, sorry. if I have a value here, like I have 2 here, then this code doesn't run, and I keep moving on. If I don't have a value here, like if I have a 0 here, then this expression will evaluate to 0, and not of 0 will become 1, and then I will run this return false. So if I have a 0 in my number, it will return false. I hope that makes sense. It's not confusing. Now also, I've had my terminal off that entire time. So take a look at this again quickly. So if there's a 0 at the spot I'm looking at in my number, then this expression will go to 0, which means this expression will go to 1, which means this code will return false. So that's why I check for 0. Okay. Cool. So next, this is actually a fun one. So what we're effectively going to do, so while I have like some value for x, well, why am I doing that? Let's do this. You can get really creative with your for loops. This is totally valid syntax, by the way. So basically, every iteration of this, I want to check and see if prime, and if it's not prime, I have to bail, and then I have to. This is the one really weird thing with this question. I have to get rid of the most significant like decimal digit, like you see here in the sample text. Like I get rid of the 4 first, then I get rid of the 6. So you have to figure out how to do that. Oh, actually, that's not bad. I've got a method. Let's code it up. So, but first, we check prime, right? So, if this number is not prime, so p at x, like, if not p at x is true, then it's prime. So if p at x is true, then it's not prime. Then we want to bail and say, yeah, it's bad. Otherwise, we have to truncate from left. And I think the easiest way of doing this, I want to say, oh, this seems so slow. I'm going to do this a dumb way, unless I can think of a better way. The dumb way of doing this is you keep like truncating it on the right until you're on the last digit, and then you can just count how many times you have to truncate, and then just like shift that many times and like mod it, sort of thing. Like what I mean by that. This is actually fun to like work through. You can see my terminal, right? Oh my god, no. I need to show my terminal. Okay, so my idea would be something like. So let's say we've got the number. Here, let's do this. Okay, so I've got 5, 4, 3, 2, 1. Oh, this is not. Okay, there we go. So I could do something like keep shifting it over. So like I shift off the 1, shift off the 2, shift off the 3, shift off the 4, and I'd say, well, that took me like what, like 4 shifts. So then, since I know that took me 4 shifts, I could take like 1, shift it to the right 4 times, and then I could mod by this number, and that would leave me with just the truncated version. It's not that bad, honestly. I'll just code it. Yeah, sorry. I just realized that. I just saw Luke's comment now, like, we can't see the editor. I need to get better at, I need like a, I don't know, like a physical light or something that says, like, you're in your editor or you're not. I can just move this down a bit so I can actually see what you guys see. Okay. Okay, so let's actually, let's try that. So it's sort of awkward, but it's not that bad, I think. So let's count, which is the number of times you have to shift it. And I'll say, so well, here, let's go int y equals x, let me make a copy, and go, well, y has a value, y divided equals 10, and I'm just literally going to count how many times I can shift it before it's 0. So this is a bit different than how I explained it, because like in this way, count's going to end up being equal to like, oh yeah, that's just the number of digits in the number, I guess. So I guess I actually need to left shift over by count minus 1 to get the behavior I want. So I'm going to go, this is the thing I'm going to mod by, and I'm going to go for, oh, this is actually big brain. I could do, alright, ready? So look at, this is the big brain play right here. Here, let's make this mod right here. Instead of updating count here, I'm just going to build my mod as I shift my other one. So go like mod. Every time I shift my original thing to the right, I'm going to shift this mod thing to the left. And then it's going to end up being 1 too big, because I shift 1 too many times. So I have to just divide by 10 at the end. Nice. Okay, so now I've got, like, my number was, this is the example from before, like, if my number was 5, 4, 3, 2, 1, then now I've constructed this, like, mod value that would be 1, 1, 0, 0, 0, 0, and I can just mod by that to get rid of my most significant decimal digit. So I'll go, like, x equals, sorry, this bugs me, there we go, sorry, x equals x mod mod. And I just want to make sure this works for 1 digit too, right? So if we only had 1 digit, you know, this supposed to work. If I had 1 digit, then mod would get shifted once. And then, so mod would become 10. I'd divide, so mod would become 1. And if you mod something by 1, you get 0. So then we'd exit out of this loop. So this will work at the end. Cool. Okay, that's good to know. So if we make it through here, and everything was prime every time, then we're really happy, and we can return true. So let's go through our code to this point. So what did we actually do? So we did a prime sieve, or receive arithmetic, whatever you want to call it, to pre-compute all our primes. And we stored that in a global array that we can just access, which is nice. And then we had this idea where, let's make some array f, where f at I is the number of fearful numbers up to and including the point I. And we can compute that by just saying fearful number I is fearful number at I minus 1, plus me if I'm fearful. And then we came up with this method to check if a number was fearful, where we just say, do I have a 0? And if I have a 0, then I'm not fearful. Or, is one of my things not prime? One of my, like, weird left truncated things not prime? If so, it's not fearful. Otherwise, if all that was passed, remember good, then it is fearful. Okay, so then, once more, back to the actual question. I'm going to hide my terminal. I will remember to actually open it this time. You'll notice they give us t, which is the number of test cases, and then they give us, what was this again, a bunch of numbers n, and we have to say for each number n, like, what are the number of fearful numbers that are not greater than n? So that's as simple as querying our f array, which is really nice. So let's do that, and ready? I'm going to enable my terminal just like that. There we go. I will remember. So now I can do, let's go here. Yeah, sorry. Make a bit of space here. So now we can actually, it's funny, we've done all this work and we haven't actually taken input. So we can read in the number of test cases. Now here's an ancient C++ secret. Instead of doing something like this, where you go like, int this equals 0, tt less than t, t++, and doing all that code, that's like way too much for me to type. Instead of that, you can do this, while t minus minus. If you do this, your code will run exactly t times, but it has the weird behavior that it will actually mutate your t value. So if you're relying on this t value elsewhere, you don't want to do this. But it's kind of a hacky way to type less code, so it's fun. So once we're in here, we're going to read in our n, and now it should be as simple as printing out f at n. Because we said f at n was the number of fearful numbers up to and including n. So if we didn't mess up anything, somehow, then this should just work. The other thing that I always watch out for before submitting any problems like this that involve number theory is checking the bounds. So we see here, our bounds are pretty small, like, we only have to worry about numbers up to 10 to the 6, so we don't have to worry about, like, using longs. Or, like, and like, when I say that, I mean, we don't have to worry about our numbers, like, overflowing regular integers, which is good. So that seems to work. Let's copy a test case as well. So once more, come here. Let's go. We've got this very tiny test case. And the output we're supposed to get is 1, 2, 2. So let's see if we can get that. So go here, in, paste that. Is that right? Oh, sorry, you guys can't see my terminal yet. Ha ha ha, there you go. Sorry, I'm just pasting in the input. Cool, save that. Okay, moment of truth. If I run this guy. So I have to compile it first, of course. But if I compile it, and I run this guy, oh, runtime error. But see, this is pretty cool. So this is really nifty. So let's say I was your average Joe, right? And I just said I compiled my code with G++, right? And I ran it, just like this. Then I just get a segmentation fault. But if instead I compile my code with this real nasty looking macro that I made, then it gives me all these extra like runtime error information and stuff. Like it'll tell me if I overflow, it'll tell me if I access out of bounds. It's like super useful. I highly recommend compiling with a nasty thing like this. Like the things you actually need are Actually, maybe I'll even talk about these at some point. Like, there's a reason why I use like each one of these things. But sorry, I don't want to like get cluttered with that right now, I guess. So let's look back at this. So the error we got was runtime error, signed integer overflow. So why is that overflowing? Really? Does that overflow? No way. No way. I don't believe that. Wait. Here. It's always good to have a Python terminal handy. Oh, that's funny. Okay, wait. Is that really? 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, I'll be damned. That actually overflows. So it looks like I think we actually It's pretty random. It's pretty funny though. I think we overflow right here when I do my trick, because if we have a prime that's like almost as big as n, right? Then I'll do I times I, so it can almost be as big as like n times n, which would be just out of bounds for an n. Yeah, that's fair. Okay, so what I'm gonna do. So it's actually funny, in my template that I use, I actually do define int long, but this is like well regarded as like something you should not do. So the standard thing most people do is they do define ll as long, and then we can just replace all the ints in our program with LLs, which will be longs. So let's do that. Since I'm in Vim, I can just select everything and go int ll global, bam. And you have to watch out, your program will not compile if main's long, so you have to change that. Okay, looks good. See if it compiles. Do we pass the sample? 1, 2, 3. Is 1, 2, 3 what they want? It is. I think that's not right. Yeah, it's 1, 2, 2. Interesting. Wait. Wait. That's really bizarre. For 1, 2, 3. Sorry. For us to give a bigger answer for the last one, that means we're saying that 4 is fearful. But 4 definitely can't be fearful, because for 4 to be fearful, it would have to be prime, but 4 is definitely not prime, so something really janky is going on. So let's figure out what janky nonsense is going on here. Okay, so this is easy to check. We can just go. What's a fun place to stop? We could go. Let's break at line 50, just for fun. Okay. So we go GDB a.out, break on 50, run in. Okay, cool. So now we're inside GDB. So I can see where I am in the code. And now the thing I'm curious about is my... Oh, come on. Oh, I forgot how to do this. It's like, So, if arrays are too big, then you can't print them in GDB. So I think you have to use X instead, which allows you just to examine memory. So, if I examine the memory of P... Oh, come on, I want to examine though... Is it like this? 5 bytes? No. I just somewhat forget the syntax. No, not like that. Oh, come on. Okay, you know what? Screw it. I'm gonna do this one just for the ones I care about. So let's check your obvious things like P at 0, not prime. P at 1, not prime. Let's go P at 4 is not prime. Okay, so it looks like our sieve is working. So the problem then is probably in our fearful. So if we print like fearful of 4, it thinks 4 is fearful for some reason, which is very bad. So why does it think that? So we can find out pretty easily. Let's put a breakpoint on fearful. So if you're in GDB, you can do B and then type a line number or a function name, and it will put a breakpoint there. So then if I call this function, oh, it does not like that. Oh, that was too next level for it. We just have to. Okay, I can just do this then. Wait. So let's go. Yeah. I'm gonna have to use a sneakier technique. So you can attach conditions to check to breakpoints in C++. So what I want to do, I'm curious about what my fearful function does when n is equal to 4. So I could do break at fearful if n equals 4, I believe the syntax is. And it can't find it. That makes me sad. Really? Oh, because it's x. It's not n. It's x. Okay, wait. So break at fearful if x equals 4. And then if I run this guy... It's hanging forever for some... Oh, because I haven't... What? No, it shouldn't hang. What? Why is this not working? Ah! No? Okay, wait. This is just being mean. Okay, new plan. When in doubt, try again. Here. So let's just do break fearful. I just want to have like this work at all now. Okay, that works. Okay, cool. So let's go. I'm more curious in... Wait, why is this all exit 0? What? Where is this being called from? Oh, wait, so I'm using a bunch of useful GDB functions here that are worth learning. Like, L shows you where you are. Where shows you like what the call stack looks like. So you can see I'm in the fearful function and I was called from main. And if I'm curious about like, hey, what's at main at 47? I can go like L main at 40. I probably should do L47 because I only have one file, right? Yeah. And that'll show me this. I equals 2. That seems fine. Why is... Interesting. Okay, wait. Let me... So I'm here right now. Oh, go figure. Okay, wait. Wait, I'm inside fearful right now, right? Yeah. What is my X? 14? Don't want that. Okay, you know what? We're gonna have to do something hacky. Let's do... If for whatever reason you can't get breakpoints to work in JDB, a really awful kind of workaround you can do is you can just do like, if, watch this. If X equals 4, CO cat. And now, in my debugger, what is that? That's line 23. My debugger, I can go break 23. Oh, wait, I have to compile first. So break 23, run, bam, I'm here at X equals 4. I can actually debug like how I want to. So let's see. So 4 doesn't have a 0 in it, which is good, but it's definitely not prime. So we should go through here, and we should get... Whoa. How do we instantly skip to the end of that? Oh! I'm so dumb. I'm so dumb. Okay, so consider that when we checked for zeros, we actually modified X. So all we need to do is go int y equals X here instead, and use Y. Now inevitably that'll actually mess up this, so let's make this like Z. Just need lots of variables. There we go, nice and easy. You know, I trust that. Let's see if this works. Oh, except it's gonna print this a lot if I don't comment this out. Okay. Hey, that's the correct answer. That's what we want. So let's get rid of our gross like debug lines. Oh, wait a minute. I've had no terminal for a long time. I'm so sorry. I think the chat has like a really big delay, so I don't find out for like a long time after. What you guys missed out on with my ranting, although you probably heard it, was actually it was just me debugging in GDB and suffering. But GDB is awesome. You should learn GDB, even if it's bad. But the problem ended up being when we were doing this thing here. I previously just had this as using X like directly, like this, and that meant that X would go to 0, and then everything here would just like instantly exit because X would already be 0. So I have to make sure that I use a different variable so I don't modify X. That's all it boiled down to. And if we run this, we see it gives us the right answer. So let's try submitting this guy, see if we can get some ACs in here. So let's do this and this. Submit solution. Ooh, that's not what I want. Do I have to do a file? Oh no, I can do this. Okay, wait. So let's not do Ada, because Ada is kind of gross. Let's see. I want to do C++. Oh, they don't. That's kind of sad. They don't support C++ 17. That means I can't use my fancy template. Here. Oh. Please log in. Oh, come on. You can see my Spodge handle. Okay, that means I have to reopen the question. Let's go here. Okay, submit a solution. Back here, C++. hoping to get AC. We should cross our fingers now. Come on. AC, A! Nothing feels better than an AC. Look at these AC greens. Ignore my wrong answer yellows or oranges. Okay, so that's this one. I think that pretty much brings us to the end of our time. Actually, I'm in Calgary, so it's like actually no, I guess it's way later for you guys. It's like 9:20 for you guys. It's 7:20 for me, so I'm gonna go have dinner. But I highly encourage you guys to try this next problem here. So it uses sieve of it doesn't use sieve of Erythronius directly. It uses a slightly modified version, but it's the same idea. So if you understood how the sieve works, you should be able to modify it to make it solve this next question, and it's like really fun. And these other questions are really good too. But yeah, I hope you guys enjoyed the event. The recording of this will be posted after. I guess the lesson of the event is need to make sure to show my terminal more, so I apologize for all like the invisible terminals. But yeah, hope you guys liked the event and hope to see you soon. That's all.